Okay, good morning, everyone. Welcome back to E379A. A couple of announcements. Actually, problem set number 2, of course, I think everyone knows is due on Thursday. I'm going to go through the feedback, which we now have on problem set number 1, which came in last Thursday. Just a reminder on solutions, I may not have said this earlier, but because we have up to 1 week on late homework, we don't hand out the solutions until the week after the problem sets normally come in. So what you'll see is a handout on Thursday. Where's Ed? Is Ed here? Not yet. Our TA should have that over here, but that'll be the solutions for problem set number 1, because we'll close off any homework on problem set number 1. The only time we won't delay it a week is problem set number 4, which is basically the one right before the midterm, so we'll give you the solutions immediately. There'll be no late homework on that. And just some announcements. I promised last time on the tape aheads I would tell you when, and TV actually have this printed out so we could come on down on the overhead here and see this. But we have a tape ahead for the lecture of February 1st, which will be on Thursday, the 27th, so that's a week from this Thursday. And it'll be right after class over here in the Skilling Auditorium, that tape ahead, from 11 to 12:15. Okay, so 379. So if you want to come live, you're welcome to do that. So you basically get 2 classes in a row that Thursday. Some of you sometimes like to have a live lecture so you can ask questions. And I'm going to do that again on about 2 or 3 weeks later, Thursday the 17th. We're going to tape ahead for the 22nd. Again, I have to be out of town. I have one other tape ahead that I'll tell you about later that isn't quite solidified yet, but those seem to be the 3 tapes we'll have this quarter. I want to mention one of the things that came back in feedback is kind of a non-technical thing, but what we have is that it's great. A lot of people are asking questions here in class. Apparently, I can't see it. I didn't realize, but you have microphones on the back of the chairs in front of you, and we are live on TV. We do have a good 15, 20 students in TV land, and they can't hear the questions. And so I'm getting that in feedback. They really would like me, and as well as you, to make an effort to try to get the microphone up and ask the question in. I'm responding to the question, but they're not able to hear it. And in this particular class, we do have a lot of TV students, so there's a lot of people out there that you can't see. Many of them are in remote places, so it's impossible to drive here. So do try to think about them. They may have the same question you have and would like to hear it. What I have on problem set number 1 in terms of feedback was that people were taking between 1.5 to 8 hours to do the homework, so gauge yourself in that set. Most of the people really were saying 2 to 2.5 hours. Now, I'm pretty sure that's going to go up because the homework assignments get a little harder as we go through the class. I try to target around 10 hours on the average, so that'll happen later in the quarter, so it's coming. We get into chapter 3, you'll see that the problems are just a little more involved because we've built now enough concepts that we can start to put them together. So you need to think a little bit more. So we were light here, clearly, but that's typical of the class. It'll gradually increase week to week, and that's when I think you'll see some of the most difficult assignments are after the midterm, where you're actually asked to design equalizers in MATLAB or such, and that will take you a little longer to get some of those done. Okay, so in any case, no one seemed to be having problems with keeping under 10 hours here, and almost everybody was just a couple hours on homework set number 1. We have what we have seen is that some people were talking about the book and the notes. I have class lecture notes. The book basically has everything, even the examples that I do in class, so you can get the details there. Some people are having difficulty, say, being able to write down everything in lecture because I'm talking, I'm writing, and you may be 30 seconds behind with your hand trying to follow all of that. You really don't need to take notes unless it's something like I say, well, and you should know for the midterm. I'm sure everybody will have their pen going on that, but as far as all the technical material, it's in the book, so you can relax a bit in class and try to listen. And if you are reading ahead, you'll see that. But I got quite a few feedback from people who are saying, I can't get it all down. It wasn't intended that you actually try to write down everything I say. It is all in the notes. And if you happen to bring the notes with you to class, if you're actually looking through the appropriate section for whatever lecture, which you get from the course syllabus, you'll actually see a lot of the things. In fact, there's more detail in the notes than there is in the lecture for that. So that may help you on note-taking. What we had was one interesting technical question came up on match filters. A lot of people were asking about match filters, so let me just spend a second or two on that. The concept is fairly easy in that we have some kind of received signal, and simply what we're saying, if I look at one of the match filters for the basis set, let's say, well, it's some phi sub n, essentially we usually offset it in time by capital T units. Well, you get something like this. When you get to complex signals later, you'll see me putting a star there all the time. That just means complex conjugate. You can forget that for now. It's the filter reversed in time. If you actually look at the Fourier transform of this, it would have the same magnitude as the original basis function. Its phase would differ because of the reversal in time that occurs here. And then we sample at time t equal to capital T. Now, obviously, what's going to happen is if we send messages delayed T units in time, then we're going to delay the sampling capital T units in time also. And so a succession of messages would correspond to successive samples at the output of the match filter. And I think everybody kind of understands this graphically and as drawn here. But the question that comes up is, well, actually, you are sampling at the symbol rate if you do that. So some of you are thinking ahead, and we are going to get to this in Chapter 3, where we send successive messages. You're sampling at the symbol rate even if the bandwidth of these filters is more than half. That's somewhere. Most of you in this basic DSP course have seen the famous sampling theorem. If you're trying to convert an analog waveform to discrete samples, you have to sample at twice the highest frequency, right? Everyone, I think, has seen that theorem. Here we may be sampling at less than that rate. And it is okay to do that when you have a match filter and we have a signal that's constructed by adding white Gaussian noise to a modulated set of basis functions where we modulate exactly also at the symbol rate. That is okay to do that, and this is sufficient, even though it may not be twice the highest frequency. Now, some of you are looking at it and say, well, you know, that's kind of curious. Well, okay, we have this special filter that we've placed here. Suppose in reality I couldn't implement this filter in analog like this. Maybe this is difficult to actually implement this basis function. How would I do it? What I would do is I'd take y of t, and I might go through some kind of low-pass filter. Okay, just standard garden variety that kind of cuts off high frequencies above the signal. And what I would do is I would actually sample at some multiples, let's say of t over, let's say, some value p, where p is an integer, and L would represent all possible samples. So I'm actually subsampling the signal. And I would pick p to be large enough that it would be twice the highest frequency in this particular case. And then I would use those samples, and then I'd probably finish off the match filter over here. Because digital filters, typically today, where everything's integrated on chips and done in discrete time, it would be easier to actually implement the exact characteristic in a digital filter that I could program somehow, set the coefficients, than it would be to do it in an analog filter. So I'd run through just basically any old low-pass filter that pretty much cuts off the signal. And then I have to oversample. In this case, I would have to sample at twice the highest frequency, and then I could go ahead and implement digital match filter over here. If this is YK, I'd get YK also in the system. So that's how you might implement exactly the match filter. So that was kind of a neat question. Several people asked it actually on the feedback, and that was really the only technical question we had. It was mainly on hours of time and the microphones and such that came back. Yes, sir. Please use the mic. I'll forget eventually, so remind me if someone's asking a question, they should use the mic. Yeah, go ahead.
From an SNR perspective, does it how does doing it in the digital domain affect the sort of derivation in the notes about using a matched filter to maximize the SNR leading into
Doesn't change it at all. Yeah,
Doesn't change
that property would still hold.
Okay.
Any other questions? Okay, well then for today, we're going to be talking about PAM and QAM, which are two of the most heavily used modulation types for the additive white Gaussian noise channel. And before I get quite into that, I'm just going to do a minor review of last week on the AWGN, hopefully to kind of set up everybody. We are going to be in sections 1.5 and 1.6 of the notes today. We're probably going to finish off essentially what I'd like to cover in Chapter 1 today, but what will happen in Thursday's lecture is kind of a review as well as an introduction to Chapter 2. So we're progressing through the notes, and that's pretty much consistent with the outline, the syllabus that you have for the class. What we saw last week is that we could replace the additive white Gaussian noise channel, the continuous additive white Gaussian noise channel, with a discrete version without any loss of information. So we'd have a vector, which is basically the data symbol itself that's transmitted, add to a vector of Gaussian distributed noise components, each of which is independent of one another, and each has variance n0/2, which is sigma squared for that noise. We define a quantity called the signal to noise ratio, which is the energy per dimension, EX bar, divided by sigma squared, the variance of the additive white Gaussian noise per dimension. And we found that the probability of error, symbol error, in other words, for an optimum receiver trying to estimate which X was transmitted, which message was transmitted, that was upper bounded tightly by the nearest neighbor union bound, which is the product of two terms, the average number of nearest neighbors, and then Q of d min, the distance between the two closest points in the constellation X, divided by 2 sigma. Or you could think of this as the ratio of half the distance between the points to the variance of the additive white Gaussian noise in any particular dimension. So it's a probability the noise is big enough to throw us over half the length of the noise is exactly how you could interpret this Q function. When you see a ratio of anything to sigma inside the argument of the Q function, that means the noise is big enough to be larger than that quantity in the denominator. And n sub b is basically the number of ways it can occur on average, the number of nearest neighbors on average. So that was our probability of error bound. We found that it was actually a little more fair to look at the probability of error normalized to the number of dimensions. So this is more fair as a comparison. And in fact, continuing that fairness idea, we talked about holding any two of the following 3 quantities constant and comparing the third, and that would give you a fair comparison between transmission systems on the additive white Gaussian noise channel. So hold 2 constant, compare a third. Hold 2, compare third. And you get a fair comparison. Okay, so that's kind of a quickie summary of what you've seen so far. Today, what we're going to talk about are some very heavily used transmission types. Pulse amplitude modulation and the closely related quadrature amplitude modulation, and then finally something we call the gap approximation, which applies to these 2 modulation techniques. So let me introduce then PAM. Basically, pulse amplitude modulation is something that is appropriate for what we call low pass, sometimes baseband channels. In other words, channels that pretty much pass everything from 0 frequency up to some highest frequency. So they're low pass in nature. No channel passes all frequencies. Okay? The additive white Gaussian noise channel is an idealization where we say that only noise is added. But of course, any realistic channel doesn't have infinite bandwidth. It's physically impossible. So it'll eventually cut off at some high frequency. Now, it might be a fiber, so the cutoff frequency might be a few hundred gigahertz before it eventually starts to attenuate signals. It could be a copper pair of twisted wires like your Ethernet connection or your telephone line, and that may only have a few megahertz of bandwidth before it starts to cut off. It could be a wireless channel where we're cut off in frequency, but it's very unlikely that we would ever see PAM used on a wireless channel because almost everything is modulated to some frequency, so it's not a low-pass channel. Typically, low-pass channels tend to be wired types of systems rather than wireless types of systems. And PAM is kind of the modulation of choice for such channels. And it's a one-dimensional transmission system. So capital N is equal to 1. It may have a lot of messages, M, and we will write it as 2 to the B, which, because N is equal to 1, is the same as 2 to the B bar. Remember, B bar is just B divided by N. And B bar will be greater than or equal to 1 in pulse amplitude modulation systems. And the idea for transmission is pretty simple. In the PAM system, it starts by looking at the first or smallest number of messages, which would be 2. In that case, B is equal to 1. And those two messages will be equally spaced with respect to 0. And we'll see symbol values of D over 2 and minus D over 2. Now, technically speaking, I could use this with any type of normalized basis function. Since I only have one basis function, it's clearly an orthonormal set as long as it's normalized. And that function could have bandpass characteristics. It could be up at some high frequency, and this analysis, everything I'm going to show you, would still apply. But typically that's not the case for PAM. Typically the basis function is some kind of low-pass filter. But you can think of this constellation being used with any normalized basis function whatsoever. And you can see that it's characterized by a distance between the points D, so I call the positive point D over 2 and a negative point minus D over 2, so that the difference between them is distance D. Okay, and that is pulse amplitude modulation for two signals. Now, sometimes it has a special name. In the case of only two signals, you'll hear this called binary antipodal signaling, bipolar signaling. There's a lot of other names for it, but it's a special case in all of those other names of pulse amplitude modulation. Clearly the distance is D. If we know this is sent over an additive white Gaussian noise channel, as long as we know the power spectral density of the noise, which happens to be the same as the variance per dimension, sigma, we could immediately compute the probability of error. It'd be P sub E would actually be equal to the number of nearest neighbors, which is 1 on average times Q of D over 2 sigma. And we'd have the probability of error. Now, why this particular structure? Well, for a given amount of energy, putting one signal at plus a level and the other signal at minus level basically gives you the maximum separation that you can get for that amount of energy. And higher D, smaller probability of error. Now, what happens when we go to 2 bits or 4 signals is we keep the spacing the same in pulse amplitude modulation. So that means that this signal gets added at 3D over 2, and this one gets added at minus 3D over 2. And so this would be the set of 4, a valid PAM constellation. This particular constellation with 4 points is sometimes called 2B1Q transmission. 2 bits for 1 quaternary symbol. Okay, so the Q is quaternary, that means 4 levels being transmitted. Okay, now the concept just extends by keeping points equally spaced, so each time we add new points on both ends, which are d, distance d from all of the other points. And we continue that out on both ends, and what you'll see, I should have a dot, dot, dot here. The last point is always m minus 1 d over 2 over here, and it'll be negative that over here, m minus 1 d over 2. So if m happened to be 8, which would be 3 messages, okay, you would see minus 7/2 here and 7/2 over here. I'd have 8 messages. If m were 16, I would go all the way out to 15/2 d on both sides, and I would have 16 equally spaced points along a single dimension. That's pulse amplitude modulation. Now, typically what happens is these messages are assigned values, and usually they're assigned from the most negative signal we call x0, and then x1, and we just continue all the way up.